Okay, the next talk in the session is on stochastic mixability and fast rates. It's by Nishant, Mehta, and Bob Williams from the Australian University and NICTA, and the talk is given by Nishant.
All right, so thanks everybody for coming to the talk, although it's single track, so you don't have a choice. So to begin, this talk is about obtaining fast rates in statistical learning, by which I mean the IID stochastic batch setting. But the main condition that we use actually comes out of online learning, and in particular it comes out of prediction with expert advice. So I'm going to first briefly explain this very old game, because it'll naturally lead into the main condition that we use for our work. So in prediction with expert advice, we have learner playing a game over T rounds. And in every round, we have K experts that are going to provide some predictions. So it might be stock predictions. And learner is going to mix these predictions in some way based on empirically how well these experts did with respect to some loss. And then nature is going to reveal an outcome. And by the way, the experts in nature can all be adversarial. And finally, once we have the outcome and the actions played by everybody, everybody suffers some loss, right? And so the goal of learner is to have low regret, which means that learner wants the cumulative loss of learner to be as close as possible to the cumulative loss of the best expert, right? And so this is a natural notion of regret for this game. And you can sort of get a geometric understanding for how this, how the order of this regret will be for different games. So for the case of absolute loss, if we have a binary outcome game, which would have outcomes of 0 or 1, once learner plays an action, there's one of two possible losses because there's two possible outcomes. And we can plot those two possible losses in two-dimensional space. So for every action, we'll have some points in the set. And if we consider all of the actions that learner could play, for absolute loss, we end up getting this line. And the important thing is, although the analysis isn't very hard, but it's hard to give in about 30 seconds. So I'm just going to cut to the chase. The flatness of this set of sort of achievable partial loss vectors means that the minimax regret for learner ends up being order square root of t. And we consider this to be bad because there are losses for which we can get constant regret, which means that it does not grow with t at all. And these are mixable losses. And again, just geometrically, if a loss is mixable, which I'll define in the next slide, and then generalize to stochastic mixability, it turns out that we have the following picture in many cases, or most cases actually. So the curvature of this set is actually what can be used for learner to sufficiently track the best expert, basically. And we end up getting minimax regret, which, as you note, it's constant in t. It only depends on eta, which is related to the eta mixability constant, which I'll now explain. So for this talk, basically, I want to introduce stochastic mixability and show you how we get fast rates for statistical learning in this case. And I'm going to get there by first explaining mixability and then going to the stochastic version, which was introduced 2 years ago by my co-author Bob Williamson and a couple of other guys. So mixability is the following. So we have some action space, and we want the following condition to hold. So for every distribution over actions, there is some action A star that learner could play such that no matter what outcome occurs, the loss of learner is less than or equal to what I like to call the mixed loss, where what we do is we sort of exponentially map all of the losses. We mix them according to this distribution, and then we undo the mapping with this -1 over eta log transform. That's just the mixed loss under some distribution. And this is the mixability condition. This might be sort of disgusting if you don't have enough time to soak it in. So there's a pictorial version of this. This blue curve is, again, this set of achievable losses. This red curve on the sort of northeast corner is the exponentially transformed version. And if you fill in the southwest quadrant of that, this red region, the convexity of that region is equivalent to the mixability of the game. And so if that region is convex, then everything's nice, and we can get constant regret. And this is analogous to fast rates in statistical learning. And so now let me actually introduce the statistical learning setting that we're considering. It's the sort of everyday easiest setting that we usually consider in learning theory, right? When you just have n points that are labeled on IID from some unknown probability measure, you want to learn a function from a function class f, and that'll give you your estimator f at n. And the regret in this setting is simply the risk of the function you learned minus the risk of the best function within your class, right? And we know that in parametric settings, like for VC classes, we can always get regret that's order 1 over square root of n just using symmetrization, have things inequality, right? We don't use much more than that. In this talk, under what I'm going to show in a second, stochastic mixability, we can actually get the fast rate of 1 over n for parametric classes. And so since I went over online learning, there's a nice projection between online learning and statistical learning. So if you're familiar with prediction with expert advice, then the point is if we have what are called constant experts, which means every expert plays the same action in every round, but different experts can play different actions, then you can view an action as a function in statistical learning. Outcomes are like labeled data points in statistical learning. The loss is basically the same. And because we have an adversary in prediction with expert advice, that's sort of like over all of the rounds, the adversary can play a full joint distribution because they can sort of have whatever dependencies they want. In the easiest statistical learning setting with IID points, you just have like some probability to measure over xy and then raise it to the n because we have IID. Right? So things like factorize very nicely. And so we have this sort of nice connection between these two games. And you can instantiate this, but I'm going to skip this for now. So in stochastic mixability, we have the following. So we have some loss. We have a function class. We have some unknown probability measure. And we say that this triple L F P is eta stochastically mixable if the following is true. So if there is some f star, which you can assume is the risk minimizer within our class, if this f star has the following property, so for all distributions pi over f, which is again like mixing over the actions in the online learning game we went over before, the following is true. The risk of f star, which is the expectation of the loss of f star, is less than or equal to the following mix risk, which again is simply the expected mix loss, right? So I use L eta mix to refer to that loss that we get when we exponentially transform. We take the average with respect to pi, and then we undo the transformation. That'll be a loss. Because we're in statistical learning, we now want to get the risk corresponding to that. And so you have this condition here, which, again, might seem kind of annoyingly disgusting. But we have an equivalent version of this, which, again, is annoying. But I'll break that down to make it nice. So the equivalent version is the thing below. And so for every function in our function class, this nasty condition below holds, but you can break this down because the difference in losses is simply the excess loss because we're subtracting off the loss of f star from the loss of the function we're considering. And if you further look at this, this is simply the cumulant generating function of the negative excess loss, negative ZF, evaluated at eta. And of course, the CGF is very important for concentration properties, and so you might imagine that we could leverage this to get the fast rate if things match up in the right way. And it turns out that this is true. So for the rest of the talk, I'm going to be using this guy quite a bit. So just sort of remember, lambda negative ZF eta is the CGF of the negative excess loss evaluated at eta. And there'll be some pictures later to tie this together. So in this talk, for our work, the main results are the following. So there are two cases that we consider. So for finite classes, we get the fast rate where the regret decays at the rate of 1 over n. And the larger the stochastic mixability coefficient is, eta star, the smaller the regret. But that's a constant, so that doesn't matter too much. It only depends on L, F, and the unknown probability measure P. So it is dependent on the problem because it depends on the unknown distribution P. For VC type classes, we get a result which is very similar. It has the natural dependence on the capacity. So here, VCF you could view as the exponent for a certain kind of, I think the L2P covering numbers for the class. And again, we have the fast rate, we have 1 over n, and a similar dependence on, or the same dependence on eta star, right? So these are the results. And for the rest of the talk, I'm just going to go through how we get the fast rate for finite classes. And the idea is basically done with a lot more technical stuff to extend this to VC type classes. And I can explain that at the poster if you have some time. So the main idea that we want to do is, so the fast rate here that we're analyzing is going to be for empirical risk minimization. So it's for the simplest possible algorithm, that the simplest non-trivial algorithm that you might use. And so the idea is to show that for any function that has high excess risk, basically that has excess risk higher than sort of order 1 over n, we want to show that the empirical risk of this function is not less than or equal to the empirical risk of f star. Because if we can do this, then we know that ERM prefers f star, to these bad functions, and we're done, because then it can only pick not so bad functions that have low excess risk. And so this is basically the probability that we want to bound. We want to make sure that the empirical risk of the bad guys is not less than or equal to the empirical risk of the best guy, right? And so, we can always show something like this for parametric classes, which is that we can choose functions that are within this 1 over square root of n excess risk ball. This is without stochastic mixability. But if you have additional conditions like the Bernstein condition or stochastic mixability, which are very related, then we can do this thing where we can actually show that ERM will pick things within this order 1 over n excess risk ball, and that's what we want. So in order to get this, what we sort of want is for those functions that have excess risk that is increasing, so you have 1 over n, 2 over n, and so on, as we get that constant above n to be large enough, we want the tail probability to be very, very, very small. And that's what I'm going to show for the rest of the talk. And hopefully you're convinced that if I show that, then we get the fast rate. I can explain more at the poster again. But that's the rest of the talk. And so we're going to use the simplest thing that one might use within probability, which is Markov's inequality. Right? So there's Markov's. Should be familiar to hopefully everybody. And so starting with Markov's inequality and exponentiating the random variable via e to the eta s, you can write something similar, except now we have this x on the right-hand side. And it turns out that we have our friend, the cumulant generating function over here. And so this is where we see the connection to concentration. And if we write S as an average of the ID negative excess losses, the fact that we have independence is very nice. And it turns out that this probability on the left-hand side is what we wanted to bound from before. So you don't even have to look at it. The thing on the right-hand side is xn, which is the sample size, times the cumulant generating function of the negative excess loss random variable evaluated at any eta that we want to choose. So we can pick that eta to be the best one that we want. So the point of this is if you look at the right-hand side, if we can get the CGF at eta to be something like negative C over n, and if we have a way of getting that constant C to be large enough, we can get very good concentration properties because we can drive that x to be very small. So what we'd like to do is say, if we have a random variable that has excess risk which is high, we would like the CGF to be very negative, such that if we double that excess risk, then maybe the CGF becomes twice as negative, and that means that we can get very fast decay for the probabilities in question. And so the key picture that we have now is, let's consider some bad guy. It'll be some function f that has excess risk that's, say, negative, or let's say it's like C over n, right? It's known that the cumulant generating function of this guy, the derivative of the CGF at 0 is equal to the mean of the random variable. And so if we assume that we know the mean is sufficiently high, we know that the slope will be sufficiently high as well. And so we have this information already. Furthermore, because of the stochastic mixability assumption, we know that there'll be a 0 crossing of the CGF at some eta star. And so we also have information about the 0 crossing. Finally, we also know that the CGF will be 0 at 0, just because of stupid math. So, it's trivial. So we have these 2 points, and we know the slope at one area. And I want to know if we have some area where the CGF dips sufficiently below negative 1 over n. Right? And if this is the case, then we're done. And we can write this as an optimization problem, putting together what do we have. So among all distributions, for the case of bounded losses that are on negative 1, 1, that have some mean, that have the moment generating function equal to 1, equivalently the CGF equal to 0 at some eta star, what is the largest that, let's say, the CGF at eta star divided by 2 would be? And this is just an optimization problem. And to solve that, from simple duality, right? So forget everything I said so far. Remember LP duality. You have a maximization problem with equality constraints. Here's the dual, right? It's a minimization problem with inequality constraints. And the key point is that if for our problem, we have something called the general moment problem. So now we're optimizing over probability measures. And so we have infinitely many infinitely many variables for the optimization. But we've only fixed certain moments. We fixed the mean, which is the general moment. We fixed the value of the CGF at eta star, which is a moment. And we also need this thing to integrate to 1, which is a certain very special moment. And we have non-negativity because it's a probability measure. So although we have infinitely many variables to optimize over, when you take the dual, we only have as many variables as we had constraints. And we now have these sort of functional inequalities, which is very nice because they heavily constrain the optimization problem. And so I've rewritten the problem that we have, and I've taken the dual. The point is we only have 3 variables, and you just want to get sufficient control on this min problem, and that'll give us sufficient control on the supreme min problem, and that'll give us an upper bound on that dip below the curve, and it'll let us show, after you do a lot of work, I mean, some of it's sort of hard, but it's basically just like trudging through and like, yeah, taking an axe to a chalkboard. You can get it bound to this form. The important thing is mu. We're going to assume that the excess risk is high, so mu will be like 1 over n or larger. And so we're going to get that the CGF does dip well below this critical negative 1 over n line. And as eta star increases up until 1, things get better and better. And so that right there is actually the sort of proof of the fast rate. We get the concentration we wanted. And I can explain this with more pictures on the poster if you like. In the next couple of minutes, I just want to briefly talk about what happens when we don't have stochastic mixability. Because there might be many conditions that give you fast rates. But, well, actually, I guess we know of maybe 2 or 3 in the community. But the question is also, can we get a sort of converse, right? So how critical is it to have this condition? And we can say the following. So if you have your function class, and if you cut out a certain epsilon ball around f star, and consider this thing which I call f epsilon, which is the function class minus this ball, but adding back in f star. If it's the case that L f sub epsilon p is not stochastically mixable for any epsilon greater than 0, then it turns out that there will be another minimizer. And so we have a problem with non-unique minimizers. And in the last slide, I just want to refer to some work from Mendelssohn, which shows that when you have problems with non-unique minimizers in statistical learning, even if you have squared loss, which is like one of the nicest losses that you could have, you can get really bad geometry for your problem, which ends up making it almost impossible to show fast race results because you're in problems that you can often show sort of, in a certain way, you can show lower bounds of 1 over square root of n. And so in conclusion, with stochastic mixability, you get fast rates. Without it, you're in a very dangerous part of the space if you want fast rates. And I can explain this in particular in the poster in a lot more detail. And so that's the main idea of the talk, right? So we get fast rates with ERM under stochastic mixability, and this is analogous to how you can get constant regret in prediction with expert device under the notion of mixability from Pofik. And so, all right, with that, I'll just conclude. So, any questions?
Before taking questions, I'd like to ask all the spotlight speakers to start lining up here. And then now, of course, we have time for some questions.
Thanks for your talk. It was really interesting. I have a question. For infinite classes, you talk about VC dimension.
Yeah.
Do you think your analysis can extend to give data-dependent bounds, such as Rademacher complexities? Or is it tied to the analysis, the use of VC dimension?
So there's a couple of points. So one is the standard Rademacher analysis,
will give you,
I guess, is so there are many different things. So we're not giving uniform bounds. Let me say that first. So it depends on the particular probability measure that there is, because our condition depends on that. So in that sense, maybe there should be more of a connection to like a local Rademacher complexity.
Yeah.
And I don't know if data-dependent stuff for what we have here is this condition that depends on LFP. But one of our main motivations was that it turns out that at least for finite classes, that the analysis is quite easy. Like, it takes some work to go through the steps, but there's very few steps, and it seems a lot more satisfying for me to go through the steps. So in terms of data-dependent bounds, we can talk more later. I don't have a good answer right now.
Thank you.
Any other question? Okay. If there's no other question, let's thank the speakers.